I created this little code to try to gather this numerical evidence. So what I do in the first couple of lines, I define my right-hand side, note the dependency on mu. I put it all together in the right-hand side because at times it is more convenient to run it in one time. Then in a for loop, I take different values of mu, and here I'm using it as an initial condition. So I use ODE for 5, that is a forward integration in Matlab, to take my right-hand side where x is defined within ODE for 5 and mu is automatically taken to be the one from the for loop. And so ODE for 5 takes 3 information. The right-hand side of your ODE that must depend on time first, and the second dependency must be on your space on your space information. So here you have t and x. Even if I don't use t, I can still define it as depending on t. The second information is the interval of time that you want to integrate over. And the third information is your starting condition, your initial condition. So you see here I choose as initial condition 0 for x and whatever I is for y. And then I'm going to plot it. I'm going to hold, and I'm going to put a title, and I'm going to pause so that I can show you the results. And then I'm going to do something similar for the same values of mu, but instead of plotting the x and y coordinate in the same plot, the second time around I'm going to plot in the horizontal axis the time, that is the passing, and in the vertical axis I'm going to plot two things, the x coordinate and the y coordinate. So let's see what happens. This is let me try to make it bigger. This is for a low value of mu. We are almost at the point in which we have periodic orbits, only periodic orbits. So mu is very small. You nonetheless see that your trajectories with different colors tend towards the same thing. You notice that they're like bulging up in something that is almost periodic. I haven't plotted enough things or long enough to actually notice exactly where the periodic orbit is, but if you add arrows, you notice that the purple is spiraling inwards, while the blue orbit close to our critical point 0, 0 is spiraling outwards. And in the middle between them, there is a periodic orbit. So here I'm increasing mu, and now I see that things go towards the periodic orbit much faster. The purple does pretty much just one round before being at the periodic orbit. The blue inside spirals outwards pretty fast. And it gets faster and faster the bigger mu is. Not only it gets faster and faster, now look, we don't even see the distances between the various orbits that we're plotting. They're all tending to the periodic orbit so fast they get all squished together. Not only it gets squished faster and faster, so they're dropping to the periodic orbit extremely fast, but we started with something that was almost a circle, and now it has this weird squished shape, and it almost has corners. And now mu is 5, so pretty big. It definitely is developing almost corners. And this is 10. Notice also how it's getting the periodic orbit itself that we're trying to plot, it's getting bigger. So now we have, this is the phase plane. So we have been plotting x and y, and we have lost the information about the time. So while I know in which direction my orbits are flowing, they're not enclosed in the information here. So now I want to change my plot, and now I'm plotting in the horizontal direction the time, and in the vertical direction the x and y coordinates. So now I start at x equal to 0 and y equal to 3, and you notice how they follow each other and they look quite periodic towards the end of it. But mu is very small, so it actually takes a lot of time for them to be getting closer and closer to the periodic orbit. but they also look very smooth. Then I have increased mu a bit. You see that the red orbit is squiggling a bit, and then it deforms more and more. We notice more and more that we get to a periodic orbit extremely fast. In the first time, the first calculus of oscillations were notably different. Here, the second and the third oscillation look exactly the same. I mean, if we were being very precise, we would notice they're slightly different, but very slightly. So for mu equals 1.8, we already have something that tends to a periodic orbit very fast, and a periodic orbit that one of the two components changes quite abruptly. You see how it goes from like something lower than -3 to something higher than 4 in a very short span. And the more we go up with mu, the more you notice that this system spends very little time moving a lot in the y-coordinate, and then a long time in which it's almost stationary, and then it bumps again, and then it's almost flat again. And this gets worse and worse the bigger mu becomes. So in this plot, you notice the speed at which your solution is moving on the trajectory. When we only plot the trajectory, you notice the shape it has. Here, you notice the speed as well. So in our trajectory, we notice that we're moving in the red coordinate, that I think is the y, very slowly for a while, and then we bump up and down. And then we are again very slow, and then we bump down and up. So there are moments in our system in which we're moving very little, and moments in which we're moving a lot. And this was all that I wanted to talk about.